All right, so the other day we started talking about the law of conservation of energy. Okay, of mechanical energy, that is. And we looked at roller coasters and things falling and stuff like that. Okay, but we didn't get to a very simple example of the law of conservation of energy, and that is the pendulum. Okay, this is my ghetto physics demo for both pendulums, and you're going to see it a lot in the next few weeks because it's also good for circular motion. This is me saving taxpayer money left, right, and center. Okay? If you want better demos, write your MLA. Tell them, stop cutting money from education. My teacher is using a drawstring from his own hoodie and a roll of tape as a demonstration, please. Yeah, okay. So, if I have a pendulum, okay, and I take it away from its center, which we call an equilibrium position, okay, if I pull it away from there, what have I done? Increase potential energy. I'm thinking of a four-letter word, starts with W. You're absolutely right on that, but work, yeah, done work. I've increased and changed its mechanical energy, specifically its potential. Okay, if I let it go, what's going to happen? It's going to swing. Okay, so that potential energy is going to convert into kinetic energy. Will it go on forever? No. In the perfect physical world? Yes. In the perfect physical world, that will go on forever. Okay, because there would be no friction, there would be no energy lost in the pendulum. An ideal pendulum is what they call it. Okay, would then ideally swing forever. All right. In the real world, that doesn't happen, but they're close. Okay, if you build a reasonably efficient pendulum, it can swing for hours. Okay, before it really starts to slow down. Okay, this one I've been giving energy to. I stopped about 10 seconds ago. Okay. Is it still swinging through a fairly consistent arc? Okay. Why do you think we use these to keep time on clocks for so long? Okay. A pendulum will swing through that arc, okay, for quite a while and can be used to keep fairly accurate time. Okay. As clock-making technology progressed, okay, because the earliest grandfather clocks, what you did was you pulled the pendulum away to a certain mark that was on the clock and you let it go, and it would swing for a while, and then if you noticed it wasn't swinging fully through that arc anymore, you just put it back and they had to do that. So they didn't keep the most accurate time. So what they did is they put a spring, a coiled spring, on the pivot point, and then you would wind the clock each morning. Okay, you'd have like a key that would go in and you would turn it, okay, and that spring would keep adding elastic potential energy, converting elastic potential energy into kinetic energy that would keep the pendulum swinging more consistently for a longer period of time. You'd only have to wind the clock once a day, okay, as opposed to having to keep the pendulum going at the right pace. Okay, but they reliably swing back and forth and reliably convert one form of energy into another. Okay? Now, if I'm looking at this particular example, I've got a 250 gram pendulum. Okay? At its lowest point, it's 5 centimeters above the floor. Okay? At its highest point, it is 25 centimeters above the floor, and it's 2 meters long. Okay? Now, the length isn't going to affect what we do, but the length actually also affects the period of the pendulum, which is how long it takes for it to make one swing. I'll show you. Okay? A really long pendulum, okay, takes quite a while to make one swing. A short pendulum swings back and forth a lot faster. Okay, so it affects how long it takes, but it doesn't affect the energy, okay, at all here. All right, so for part A of this question, would I be able to calculate the mechanical energy of the pendulum relative to the floor when the bob is at its highest point? So that is out here before it's released. What kind of energy does it have here? Potential. Just potential. Okay. So if I wanted to calculate that, then I would just go EP equals actually the mechanical energy, which equals m times g times h. So we take our 0.250 kilograms, multiply it by 9.81, and then multiply it by the height, which is a terrible number. They chose 0.25 for two different things, okay, but such is life. Okay, so if I do that, So 0.25 times 9.81 times 0.25. Okay, so that's the total amount of mechanical energy at that point. It is also the total amount of mechanical energy. Where else? Everywhere, yeah. Anywhere along the arc that pendulum swings, that is its mechanical energy. Okay? It will always have that much. How much of it is kinetic and how much of it is potential is always going to change. Okay? But that is our total mechanical energy. So 0.613125 joules. Now we only have 3 significant digits, so I guess we'll take that off. 0.613 joules. Okay, what is the mechanical energy of the pendulum relative to the floor when the bob is at its lowest point? Well, we just discussed that. What number is it? 0.613 joules. That number is not going to change. Okay, what's the kinetic energy of the bob at its lowest point? It would be if the lowest point was at a height of 0. This is a trick, right? They tell us that its lowest point is still 5 centimeters above the floor. Okay, so to do that, I would have to say, okay, 0.613 is my mechanical energy. That equals my kinetic energy plus my potential energy. And I can calculate the potential energy at this point because I know the mass. I know it's still 5 centimeters above the ground, okay? And I would just have to subtract it from 0.613. So m times g times h, and that'll give us EK. So 0.613 minus the mass, 0.25, times 9.81, times the height, which was 0.05. Okay, so what's left there is 0.490 joules of kinetic energy. So most of it is kinetic, okay, which makes sense. It's not very high off the ground anymore. All right, part D wants to know the speed of the pendulum at that same point. Can I calculate that now? I can, because that number I just calculated is my kinetic energy, which equals 1/2 mv squared. And I know the mass already. So if I want to find v, I'm going to take the square root of EK divided by half of m. So that'll be 0.490 divided by 1/2 times 0.25. All right, so it's moving at, we got 3 significant digits there, so 1.98 meters per second. All right, is that still a law of conservation of energy question? It is, right? We used, once we found that mechanical energy, we used it for more than one point along the path of travel. All right, questions on how the pendulum works? Does it work just like a roller coaster? It does. Okay? All conservation of energy questions come down to the same thing. Initial equals final. Okay? All right, I would like you guys to try question number 2. Okay, we have a model rocket that has a mass of 3 kilograms. It's fired so that when it's 220 meters above the ground, it's moving at 165 meters per second. At that point, the fuel runs out. Okay? So if the fuel runs out, it is now in unpowered flight. All the work has been done. It now has all the energy it's ever going to have. Okay? No more is going to be added or taken away. Okay? Assume that the effect of air friction is negligible and that all potential energies are measured from the ground. Okay? It wants you to calculate, sorry, I got to shrink this so you can see everything. Okay, it wants you to calculate the mechanical energy when it's 220 meters above the ground and moving at 165. Okay, when it reaches its highest point, what will its gravitational potential energy be? How far above the ground is it at its highest point? And how fast is it going when it hits the ground? Okay, so we're just shooting a rocket straight up in the air and letting it come straight back down. No friction. Okay, so it's a conservation of energy problem. All right, give you a few minutes on that one. All right, so for the first two here, okay, it wants to calculate the mechanical energy of the rocket when it's here at 220 meters and moving at 165 meters per second. So mechanical energy is simply the potential energy plus the kinetic energy. We'll call those our initial values, but do I need to put an initial beside this one?
No.
Not really. I mean, I can if I really want to indicate it, but we know that number is constant. It's going to stay that number through the entire flight of the rocket now. Okay? So we're going to go m times g times h initial plus 1/2 mv initial squared. Okay? And so we're going to have, what was the mass? 3 kilograms times 9.81 times 220 meters plus 1/2 times 3 kilograms times 165 squared. 3 times 9.81 times 220 plus 0.5 times 3 times 165 squared. Okay, so there is our total mechanical energy, 4.73 times 10 to the 4 joules. Okay. Everyone okay with part A? Can I use that answer again? 4? Yep, for part B. Don't have to do any more math. I just have to understand that that is the mechanical energy of the rocket at all points in its flight from this point forward. Okay, so when it asks what is the gravitational potential energy at its highest point, well, at its highest point, it doesn't have any kinetic energy. Anything that goes up stops for an instant at its highest point. So its mechanical energy would be all potential at its highest point. All right, how far above the ground is the rocket at its highest point? How many people have done C? Okay, maybe I'll give you guys a couple more minutes on that one. Here's the hint. All of that energy is now potential at its highest point. Okay, so you might get to use that number again and again. Okay, so if we're looking for the highest point, the actual altitude at the highest point, this number, as we established, is my gravitational potential energy at that point. So I'm just going to say that EP equals m times g times h. Okay, I'm going to divide both sides by mg, and I'm solving for the maximum height of the rocket. All right, so that will be 4.73 times 10 to the 4 joules divided by 3 times 9.81. Okay, so there's our maximum height. That's exactly 1 mile, 1,607 meters. Okay. Everybody all right with that one? But we would have only 3 significant digits, so we would be looking at 1.61 times 10 to the 3 meters, okay, for our answer there. Okay, do I get to use this number for part D?
Yep.
Yes, because now when it's on the ground, this number is my kinetic energy, because on the ground I have no potential. All my energy is now kinetic. Okay, and I do a very similar calculation to this one, except I make it EK instead. Alright, so I just divide both sides by half of m, square root, and I'll have b. Okay, so I'll have 4.73 times 10 to the 4 joules divided by half of m, so that'll be 1.5. Okay. Okay, so it's going 177, 178 meters per second when it hits the ground. Okay, everybody all right with that? Okay, are these making sense? Okay. Are they pretty like cookbook? Like follow the instructions, I'll get the right answer? Okay, I would like you guys to try number 3, and then I got video to show you for number 4. Okay, so in this one here, we have a situation where our initial mechanical energy is equal to our final mechanical energy. We know that because they told us ignore the effect of frictional forces. In other words, energy is conserved. Okay? Now, what we know is that we know the mass, we know the initial speed, which is quite slow, okay, and we know the initial height. We are looking for the the kinetic energy at the top of the second hill. So we're looking at this situation here, okay? This is our initial point, and this is our final point here. Right? We're looking for what is our EK final. Just so you know, this is not how I would ask this question. I would ask you for the final speed, okay, rather than the final kinetic energy, which is one more little calculation. But, okay. So what we're going to have here is EP initial, which we know we have, okay, plus EK initial, which we know we have. It's going to be pretty small, but we've got it, okay, equals EP final plus EK final. All right, and so that's going to mean M times, actually, if we're looking for EK final, what should I move right now before I put in the formulas? Right, I should move EP final over to this side. So I'll have initial potential plus initial kinetic minus final potential equals final kinetic. Okay, so now that'll be M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals EK final. Can I cancel the masses in this one?
Yes. No.
No. I can't cancel the masses in this one for this reason. I'm looking for energy, and energy is joules, which are kilogram meters squared per second squared. I got to have it. And secondly, I didn't put in the formula for this. I'm looking for it, which means mass is not in every term. Okay, had I written out the formula for this and said I'm finding part of it, V, then I could cancel the masses. Okay, because the speed is only dependent on gravity, not on the mass. But the energy is dependent on the mass, so I have to keep it in there. All right, so we're going to have 840 times 9.81 times 85 meters plus 1/2 times 840 times 0.2 squared minus 840 times 9.81 times 64. Okay, that'll give us our final kinetic energy. Okay, there's my final kinetic energy, 1.73 times 10 to the 5 joules. Okay, everybody all right with that? Okay. I'm going to give you a 5-minute break, and then we're going to go on to the pole vault question. I'll show you a video of pole vault so you can kind of get an idea of how it looks. Yeah. Yeah. Yeah, but be quick. I don't like having this many people out at once. So, our next question here, guys, is going to be on pole vaulting. Now, I don't know if anyone's ever seen pole vault before, but I'll show you a video of it. Okay, but pole vault is a perfect example of many energy conversions happening in a row. Okay, When the pole vaulter runs, is running towards the pit and the bar, okay, they're building up what kind of energy? Kinetic, well, mechanical too, but mostly because they're building up kinetic energy, okay? When they get to the pit and the bar, okay, they take the pole from its running position and they plant it. There's a little box, okay, that they have to plant the pole in, right? And then the pole bends a lot, okay? Now, you have to be careful if you're doing pole vault. Okay? I used to coach track and field. I actually did a little bit of pole vault in high school until I did it wrong, and then I couldn't get back on that horse again. Okay, the pole only bends one way. If it rotates in your hands, it'll break. Okay, it has a bendy side and a not bendy side. Okay? So if you plant it right, you'll get it to bend, and then you're going to convert all of your kinetic energy into potential, elastic potential energy in the pole. Okay, the pole will bend, and then it will shoot you up into the air. Okay, again, provided you put it in the right way. Okay, if you put it in the wrong way, your kinetic energy will turn into an exploding fiberglass pole, and you will land on your head. Okay, because the pole will not explode until you are fully committed. That means you are inverted and holding onto the pole. Okay, that's when the pole breaks. Okay. So, if you do it right, the pole shoots you up into the air. So it converts your kinetic energy into elastic, then converts the elastic back into kinetic, and then into potential. And then over the bar you go, okay? And your potential converts back into kinetic, which is then absorbed by the pit, hopefully. Okay? If you miss the pit, that can also be painful. Right? Okay, so I'll show you what this looks like here. So now that we've seen what it looks like, I would like you guys to try question number 4, okay, with our 56 kilogram pole vaulter, okay. We're looking for the maximum height she can hope to attain if the speed of her approach is 8 meters per second, okay. And we're going to assume that the center of mass of the vaulter is 0.850 meters above the ground, okay. What does that mean for potential energy? There is some, initially, okay? Because we're going by her center of mass. Her center of mass is not on the ground, okay? They're saying that her center of mass is about right here, okay? 0.85, so somewhere in there, that would be her center of mass. So she's also shorter than me, okay? That sort of makes sense? Okay. All right, give you a few minutes on that one. Okay, so we know the mass and we are looking for the maximum height. Well, at the maximum height, how fast is she going? 0. So she would only have potential energy at that point. Okay, so we can say then our initial mechanical energy equals our final mechanical energy. Our initial mechanical energy has some potential and some kinetic, but our final only has potential. Okay, so I can plug in my formulas here. M times G times H initial plus 1/2 MV initial squared equals M times G times H final. Can I cancel the M's on this one? I can. I don't have to, but I can because I'm looking for a height. Okay, the height she reaches is not affected by her mass. Okay, it's affected by her speed, okay, and by gravity. So mass can cancel out here. All right, so to get final height, I would just divide both sides by G, okay, and plug in my numbers. So 9.81 times 0.85, that was our initial height here, where her center of mass was, plus 1/2 times 8 squared, that was her initial speed, okay, divided by 9.81 would give us her final height, okay, which should be 4.11 meters, yeah? Okay. Now, just so you know, I coached track and field for 20 years. I never saw anyone clear 4 meters in high school track and field. Okay, so this would likely be an Olympian. Okay, especially as it's women's pole vault. Okay, so it's like that's
getting 6 meters.
What? Yeah.
Yeah.
Okay.
Did you do pole vaulting for our track?
No, I didn't do it because I felt it was too dangerous.
Yeah.
Yeah, I wasn't going to risk people's mobility for the rest of their lives. Yeah, for that. It's also really expensive, like to get a good pole vaulting set cost about 60 grand. And if I was gonna do it, I wanted the good one, so there was less likelihood of anyone getting hurt, but in the end, it was just, I didn't want anyone to get hurt. Because every time we went to a competition, somebody got hurt. It's like rugby, in that way. So, yeah, somebody always gets hurt. Okay, now for B, describe the energy changes that occur. So we've already done that. We talked about how when they come in, it's all kinetic. And then they turn it into elastic potential energy. And then it gets turned back into kinetic. And then it gets turned into gravitational potential energy. And then it gets turned back into kinetic. Okay, so it's a series of energy conversions. Okay, is it all truly conserved? No, not a chance. Okay, the pole is going to make sound. It's going to get hotter. Okay, there's going to be air resistance through the air. Okay, so all that kind of stuff like that. That's going to result in losses of energy along the path of the pole vaulter. Okay. Hey, I would like you guys to try, oh no, that one's worded poorly, never mind. Okay, try that one. Okay, we'll end on that one for today. All right, so for number 6 here, okay, we have the average horizontal force of 12 newtons. That's how we can tell that it's not a conservation of energy question. Okay, on the bow arrow system, pulling the string back 0.30 meters, which is a distance, another thing we would never get in a law of conservation of energy question. The arrow has a mass of 0.45 kilograms. What is its speed at the target 5 meters away? Well, it's the same speed as it leaves the bow at. Okay? There's no friction here or anything. It shouldn't lose any energy on the way there. Okay? So we would just have that work equals the change in kinetic energy. Right? So we'll have force times distance equals 1/2 mvf squared minus nothing, because when it's in the drawn bow, it isn't moving and has no kinetic energy at that point. So all we have to do is solve for Vf, like so. Okay, so we would have 12 times 0.3 over half of 0.45. Square root of 16 is 4. So, okay, everybody all right with that? So just a work energy thing. Threw it in there just because I wanted to see if, hey, do we remember that if Coder gives us a force that is not a conservation of energy question? So threw it in there on purpose. It was mean. Yeah. All right. I want to give you one here that's kind of like what I told you about earlier, where I give you a conservation of energy question followed by a work energy theorem question as a part B. Okay, so let's say we've got this situation here. All right, so we have, let's say, a sled going down this hill, and it's going to start here at 25, at a height of 25 meters and an initial speed of 3.0 meters per second. Okay. I am going to want the speed here at the bottom. Okay, that'll be part A. Okay, speed at the bottom will be part A. And then we're going to say that from here to here, there is friction. There's no friction along this part. Okay, but along here, this is like the braking area. They put on the brakes on the sled or something. Okay, so this is the braking area here. And we'll say that the force of friction along that area there is going to be, let's say 150 newtons. Oh, sorry, I got to give you mass here. Mass we'll say is 60 kilograms. Okay, force of 150 newtons. Part B is how far do they slide before stopping? Okay. Okay, so for this one here, okay, we start out with a law of conservation of energy question with the sled going down the hill. Okay, so we would just have EI equals EF. At the beginning, we have some kinetic energy and some potential energy, but at the end, we only have kinetic because we're at the bottom. Okay, so at that point then I can put in my formulas, m times g times h initial plus 1/2 mv initial squared equals 1/2 mv final squared. Mass is in every term, so I'm going to cancel it as I'm looking for v. Okay, then I'm going to divide both sides by 1/2 and square root. Okay, so I'll be left with the square root of 9.81 times 25 plus 1/2 times 3 squared divided by 1/2, and that will give me my VF. Okay. 9.81 times 25 times plus 0.5 times 3 times 3 squared, sorry, 3 squared. Okay, then we divide that by 1/2, and then we square root that number. Oh, I might have put a negative in front of it for some reason. All right, so we're looking at a final speed of 5.6 meters per second. Okay, everybody all right with that? It's not a very high hill. Okay, so they're not going to get going very fast. That's part A. Now for part B, I'm trying to figure out how long they will, or how far they will travel before they stop, which is a work energy theorem question because friction is doing, or the sled is doing work against friction and losing its energy. I didn't calculate the energy, did I? I calculated the speed. Could I very easily calculate the energy of the sled at the bottom of the hill? Or at any point on the hill? Okay, I would say bottom of the hill is easiest because it's only one formula. If I want to calculate the initial energy here, that would be kinetic, okay, and I would just go 1/2 mv squared because I just calculated the v. All right, so I'm going to go 0.5 times, what did I say the mass was? 60, right? Times 60 times that number there squared. All right, so that's how much energy they have when they get to the bottom and anywhere else on the hill. Right? Now they apply the brakes, okay, and they're going to slow down. All right, so if they're going to slow down along this level part of the place they're at, okay, that's going to be force times distance equals the change in their kinetic energy because they're going to stop. So what I'll have here is the force of friction times the distance equals 1/2 mvf squared minus 1/2 mvi squared. Well, this is 0, so I can just make it 0 right away and manipulate for d. So that means I would divide both sides by the force of friction. Okay, so what I'm going to have here is 0 minus 1/2 times 60 times, actually, I don't even need to do this. Sorry guys, I totally overthought this. Do I have that number? I just calculated, right? It's 948. So I can just put that in. 0 minus 948, okay? Divided by the force of friction, which I said was going to be 150 newtons. Okay, so even simpler than that. Okay, divided by 150. Done. They're gonna slide 6.3 meters before they stop. Sorry, I made that one easier than I thought I made it. but that would be similar to the type of thing I might ask on a unit exam. Okay? The second part often throws people, because they think there's more to it. Even me, the guy made it up, thought there was more to it. All right, tomorrow, unit exam review. So my suggestion would be, show up tomorrow with some questions. Okay? And you will have a quiz. It'll be a conservation of energy problem. Okay? I'll post it later on today.